after high school, when you go to university, you learn all these important things, and one of the things that you learn is that contemporary at university. It's always that.
And then you feel very important, right?
Yes, exactly.
So you break this fight. Right.
I make fun of Barbara, my girlfriend, so she's a medical doctor.
Yeah.
And every now Okay, good. Let's start. Good morning, everybody. Thanks for being here. The particle physicists were here even before 11. Thanks for waiting in the warm room. This is a joint seminar. If it goes well, maybe we should do this more often, I guess. We'll see. And today it's a real pleasure to have Martin Schmaltz. Martin is a professor at Boston University, and we're very lucky to have him visit our group at the Institute, Josef Stefan, for about a month altogether. So he's been around already for a week and a half, roughly, and he'll be here for another couple of weeks. So if you have questions, just come across the street and you'll find him, okay? He's actually sitting in office C. Okay, I can send an email if people are interested later, otherwise I'm gonna give you the wrong information. Anyway, enough. Martin is gonna tell us about the Hubble tension, and please. Thank you.
Thank you so much all for coming, and thanks for having me and hosting me here. I would like to give a talk about the Hubble tension, a little bit of an update of what the latest situation is. I'm a particle theorist. I like to dream about theories that, with new particles that might have an impact on cosmology and might perhaps, and that's how I was motivated, perhaps resolve the Hubble tension. If I had a theory that resolved the Hubble tension, that would be my talk. I don't have one. I have lots of ideas that don't work. So I thought maybe I give you an update of what the tension is and just hint at what people have tried for resolving it, but I'm not going to be able to tell you what the Hubble tension resolution is. Perhaps somebody here in the audience will be inspired to find it. So what is the Hubble tension? The Hubble tension is we're measuring the expansion rate of the universe. We have two different ways, or we have many different ways, but two sort of classes of ways of doing it. One way uses the CMB and baryon acoustic oscillations, and I'll explain all of this. And they get this value for h naught, the expansion rate of the universe. I left out the units. It's kilometers per second per megaparsec. And we'll talk about that too. And then there's another way of measuring it, which gives a different value. And if you work out the sigmas, assuming it's Gaussian, is 6.2 by now sigma tension. It depends a little bit on who calculates. Some people get 5 sigma, some people get 7 sigma. It depends on which data you collate to do that. And if you like p-values, we're now at 10 to the minus 10. So clearly something is going on. This is not an accident. An accident would be, very, very unlikely at this point. So this is what I want to talk about. I want to talk about how is this measured first, and then how is that measured, and what can we do to maybe modify. And no, this doesn't work anymore. Where's my... Okay, there we go. So here's my outline. So first I'm going to explain Hubble's law. That's how we measure h naught using Hubble's law. And then one of the two kinds of measurements uses what's called a distance ladder. And the most prominent experiment or collaboration there is the Shoes collaboration. And, but there are some others as well. So I will spend some time explaining how those measurements work, what are the latest developments in those. Then we'll talk about the CMB and baryon acoustic oscillations, and how they determine the expansion rate. And so they use the model, our standard cosmological model, lambda CDM, and a thing called the sound horizon. I'll explain what those things are. Then I will talk a little bit about beyond the standard model physics and how that could modify this way of determining h naught. And I'll summarize that part, and if there's extra, I want to talk a little bit about the recent DESI measurements of the energy, which seem to suggest that something funny is going on with dark energy, and maybe. All right, so let's start with Hubble. We're trying to measure the expansion rate of the universe, trying to measure at the rate at which distances are getting bigger. because of the expansion of the universe. And that rate, so how quickly distances are getting bigger, is what we're calling h naught. It is defined to be the recession velocity of